Hi friends, welcome to Learn Engineering with Mira. Today we will discuss how to find out magnitude of forces acting on an object while in equilibrium by two methods, by equilibrium equations and by Lami's theorem. Also we will see how to draw a free body diagram of any given problem easily. So let's begin. Let's have a look at the first example. Suppose a shelf is attached to the wall. One side of shelf is rigidly secured to the wall, but the other side is not, which may lead to bending or even fracture of the shelf once it is full of objects. So to support this free side, chains are provided which will pull the shelf in upward direction and brackets are provided to withstand the load. And we want to find out the magnitude of reaction forces acting on supports at point O to maintain the equilibrium of assembly. Let's first of all draw the free body diagram by considering all the forces acting at point O. As we discussed, there are two supports, one is chain and another is bracket. And to draw the free body diagram, we need to find out the direction in which the free movement of shelf is restricted by each support. Because if the movement in any direction is restricted, reaction force develops in opposite direction. So first of all, we will consider only chain and ignore the bracket. Chain can only pull the object to position and cannot push. So chain in our case pulls the shelf in upward direction and restricts the downward movement. So reaction will develop in opposite, that is upward direction, and on the chain line itself. Now let's consider the other support brackets and ignore the chain. It can be considered that the bracket is withstanding all the loads acting due to objects placed on shelf and so prevents the downward movement of free side of shelf. So reaction will be in opposite direction and again it is acting along the bracket. Additionally, force F is acting in downward direction due to self weight of shelf and weight of objects placed on shelf. And this is the free body diagram of bracket along x and y axis. Rearrange all the forces without changing angles so that the tail of all forces meet at point of origin. Magnitude of force F is given, that is 400 Newton, and it is acting in vertically downward direction making 90-degree angle to horizontal. Chain makes 45-degree angle to horizontal and bracket makes 30-degree as shown here. Reaction forces in chain and bracket are T and C respectively, which we need to find out. Also, it is mentioned in the problem statement that the whole assembly is in equilibrium. Whenever it is stated that the object is in equilibrium or at rest, it means that number of forces might be acting on the object, but the direction and magnitude of all the forces are such that the resultant force is zero. And if the final force is equals to 0, object is not moving in any direction. Now, there are two methods to solve numerical of equilibrium. One is by using equilibrium equations and another is by using Lami's theorem. Equilibrium equations can be used for any kind of problem, but Lami's theorem is applicable if there are only three forces acting on the body. In given problem, only three forces are acting, so we will solve numerical using both methods and compare results. Let's start with equations of equilibrium. As we discussed, if a body is in equilibrium, resultant force R is equals to 0. Thus, the components of resultant force along x-axis and along y-axis are also equals to 0. These two equations are called the equations of equilibrium. Here x component Rx is summation of horizontal components of all forces. Similarly, Ry is summation of vertical components of all forces. So the first step in this method is to find out x component and y component of each force acting at point O. Force C makes 30-degree angle to x-axis. So x component Fxc is c cos 30 and y component Fyc is c sin 30. Similarly, force T makes 45-degree angle to x-axis, and so x component Fxt will be t cos 45 and y component Fyt is t sin 45. Third force F makes 90-degree angle to horizontal. So x component will be F cos 90 is equals to 0 and y component is F sin 90 is equals to F. Now according to equilibrium equations, summation of all horizontal components should be equal to 0. So c cos 30 minus t cos 45 is equals to 0. Here Fxc and Fxt are collinear forces but are in opposite direction to each other, so they will be subtracted. By putting values of cos 45 and cos 30, we get c is equals to 0.816 t. Similarly, summation of all vertical components is equals to 0. So, C sin 30 plus T sin 45 minus F is equals to 0. Here, F is collinear to Fyc and Fyt but in opposite direction. By putting values of sin 30 and sin 45 and F equals to 400, we get this equation. Now replace C in equation 2 by 0.816 t. So we get 1.115 t is equals to 400 and t is equals to 358.63 Newton. Put this value of t in first equation and we get C is equals to 292.82 Newton. Now let's solve same problem with another method, that is using Lami's theorem. For this method, the very first step is to find out angles between adjacent forces. The angle between forces C and F is 30 degree plus 90 degree is equals to 120 degree. Angle between force F and T is 90 plus 45 is equals to 135 degree. Similarly, angle between forces T and C is total angle between positive and negative x-axis, that is 180 degree, minus 45 minus 30 equals to 105 degree. Now Lami's theorem states that if three forces are acting on a body, each force is proportional to the sine of angle between other two forces. Let's say first force is C and it is divided by sine of angle between other two forces F and T, that is 135. Second force is F and it is divided by sine of angle between forces T and C. that is 105 degree. And the third force is T, and it is divided by sine of angle between C and F, that is 120. Then all these divisions are equal. Now the magnitude of force F is known to us and magnitudes of C and T are to find out. So let's compare the equations of C and T with F individually. After putting all values, we get C equals to 292.82 Newton and T equals to 358.63 Newton. You can observe that both methods give same result of C and T. Let's see one more problem. Suppose a truss bridge is provided over a lake. Bridge is a good example of equilibrium where various forces act on different parts of bridge like forces by water current, wind, live load due to vehicles, etc. But they all are counterbalanced by self weight of bridge or foundation or other supports so that it remains in equilibrium. You don't find same bridge moved to other river overnight, right? So today we will see a problem on equilibrium of a component of the bridge truss. Forces are acting on the joints of all connecting members of truss. And we want to find out magnitude of some unknown forces on one particular joint. Now let's have a look at the given data. Two horizontal forces of 7 kN and 10 kN are acting on joint but are in opposite direction. 2 kN force is acting in vertically downward direction. Force T is acting on inclined member making 45-degree angle with horizontal, and force C is acting on inclined member which makes 30-degree angle to vertical. Here we want to find out the magnitude of forces C and T. First step is to draw the free body diagram. As there is no direct external support to the joint, like there is no direct contact to any pier or wall, which means that no adjacent body is directly supporting this particular joint. So only the forces acting on the joints of connecting members will be included in free body diagram. So this is the free body diagram with all the forces along x and y axis. Rearrange the forces so that the tails of all the forces meet at the center. For that, extend the lines of action of forces 10 kN, 7 kN and force T, and they are meeting at the center. Drag 2 kN force and force C in downward direction so that their direction, that is angle, is not changed and their tails are at center. Now let's find out angles the forces make with x-axis. Force C makes 30-degree angle to y-axis, which means that it makes total angle 90 minus 30 equals to 60-degree angle with horizontal axis. It is given that T is acting at 45-degree angle and 2 kN force makes 90-degree angle to x-axis. As we already discussed, there are two methods to find out unknown data while the body is in equilibrium, out of which Lami's theorem can be used if only three forces are acting on the body. As number of forces are more than 3 in our case, we will solve the numerical using equilibrium equations only. The first step in this method is to resolve each force into two components, one along x-axis and another one along y-axis. First force is of 7 kN which makes 0-degree angle to x-axis. So x component Fx1 will be 7 kN and y component Fy1 will be 0. Second force is T and it makes 45-degree angle with x-axis. So x component fx2 is t cos 45 and y component fy2 is t sin 45. Third force of 10 kN magnitude acts in horizontal direction along negative x-axis. So fx3 will be 10 kN and fy3 will be 0. 2 kN force is acting in vertically downward direction, making 90-degree angle with x-axis. So fx4 is 0 and fy4 is equals to 2 kN. Similarly, fifth force C makes 60 degree to x-axis. So fx5 is equals to C cos 60 and fy5 is equals to C sin 60. We know that while the body is in equilibrium, the resultant force acting on joint is equals to 0. And so the components of resultant force acting along x-axis Rx and along y-axis Ry are also equals to 0. So let's find out Rx and Ry. As all the horizontal components acting along x-axis are in same line, Rx is summation of all horizontal components. Here 10 kN force is collinear to other components but in opposite direction. So it will be subtracted. As Rx is equals to 0, we get 0.707T plus 0.469C is equals to 3, which is our first equation. Similarly, all vertical forces are to be added to find resultant force Ry. Here also, components C sin 60 and 2 kN are in opposite direction to component T sin 45, and so they are deducted. So we get 0.707T minus 0.866C is equals to 2, which becomes our equation number 2. Subtract second equation from first one. So 0.707T is cancelled and we get 1.37C is equals to 1. And so C is equals to 0.73 kilonewton. Put value of C in equation 1 and we get force T is equals to 3.76 kilonewton.